Our survey of the solar system will soon shift its focus to Earth. That's our home planet. The Earth has many unique characteristics, not the least of which is life. But first, let's complete our travelogue through the solar system. Recall that planets can be divided into two groups of four. So we have the inner four terrestrial planets. Those are the rocky worlds: Mercury, which is closest to the Sun; Venus, which is shrouded by a thick layer of clouds; Earth; and the red planet Mars. Those terrestrial planets are quite distinct from the four outer Jovian planets, which are all gas giants. There's Jupiter, the largest planet that has violent weather and many moons; then the ringed planet Saturn; next is Uranus; and finally Neptune. The differences in the size and composition between the inner and the outer planets was a result of the Sun's radiant energy. The solar wind and high temperatures blew off most of the hydrogen and helium from the inner solar system, so the inner planets are small and they're rocky. And then the outer planets are big balls of hydrogen and helium. So in a very real sense, the solar system distilled the chemical elements, very much like a chemical distillation column. Well, the solar system doesn't end with the gas giant planets. Additional, rather mysterious objects litter the space beyond. So I want to tell you about Pluto, which is the 9th planet, as well as the Kuiper Belt, the Oort cloud, and comets. Now, Pluto is really quite an enigma. The discovery of Pluto followed a long search by several astronomers. Remember how the position of Neptune was predicted from perturbations in the orbit of Uranus? Well, by the same token, the existence of a planet beyond Neptune was predicted by American astronomer Percival Lowell, who thought he detected slight perturbations in Neptune's orbit. Now recall that Percival Lowell is best remembered for his maps of the so-called canals of Mars. He claimed that these canals were evidence of an extinct civilization on Mars, so not everyone accepted what he said. Anyway, he called the missing object Planet X, and he searched futilely for it until his death in 1916. And the search was resumed by the American astronomer Clyde W. Tombaugh. Tombaugh painstakingly compared photographic plates of the night sky taken several months apart, and he looked for an object that moved relative to the stars, but he wanted one that didn't move too much. You see, there are lots of asteroids that move significantly from night to night against the fixed backdrop of stars, but they're a lot closer to the Sun, and so they appear to move relatively quickly. This presumed 9th planet had to be beyond Neptune, so the key to discovery was to find something large enough to be seen with a modest telescope, but sufficiently far away to move slowly. So after a long period of observing, Pluto was discovered by Tombaugh on February 18th, 1930, and here are the original discovery plates, and you can see the faint object that's moved a little bit from one photograph to the next. Pluto turns out to be a strange place. It's really unlike the other planets in several respects. First of all, it's quite small. It has a radius of 1,140 kilometers. That's only 2/3 the size of the Moon. You might ask if that's even large enough to be called a planet. Well, one rule of thumb I've heard is that an object has to be large enough to be pulled by gravity into a spherical shape, and Pluto is round, so it fulfills that criteria. Now, Pluto has an extremely elliptical orbit that averages about 40 times the Earth-Sun distance during its 249-year period. And it turns out through about 20 years out of every orbit, Pluto is closer to the Sun than Neptune. And that was true for the period from about January of 1979 till very recently. During that time, Pluto was technically the 8th planet, but for the next 200 years, Pluto is going to be the 9th planet. And for more than a century, it's going to be getting farther and farther away from the Sun in its orbit each day. Now, another curious anomaly is that Pluto's orbit is significantly tilted to the plane of the other 8 planets. You can see that feature in this drawing of the solar system. Now, these characteristics have led some astronomers to suggest that Pluto might actually be an escaped moon of Neptune rather than one of the original planets. You can imagine a late-stage impact that in effect knocked Pluto into a new skewed orbit around the Sun. And there's another unusual feature. Pluto is in effect a double planet. Look at this. Its moon Charon is about half its size and is in close orbit. Here's a photograph of these two. They're gravitationally bound to each other. Now, on beyond Pluto are still more solar system objects. Remember, these are objects that are tied to the Sun by gravity. So we have the Kuiper Belt. That contains hundreds of enigmatic objects up to a few hundred kilometers in diameter. The Kuiper Belt objects are difficult to study because they're small and they're very far away. But it's possible to collect some photons that bounce off their dark surfaces. Now, from their relative darkness, they appear to be at least partly rocky. See, icy worlds would be a lot brighter than what we observe. And reflectance spectroscopic surveys of the color of these objects suggest that there may be two distinct populations. One group appears to be a bit more blue, the other group is a bit more red in reflected light. It's hard to know exactly what that means, but it suggests there may be two different compositions of rock, or perhaps maybe one of these groups has a surface coating of organic compounds. These are really difficult observations to make, but with improved space telescopes, I'm sure new observations are going to tell us a lot more. You know, some scientists have proposed that Pluto is really the largest of the Kuiper Belt objects, that it's not a planet at all. I suspect that that's just a semantic argument. You know, each of these big objects in the solar system is in effect a unique and distinctive body. What we call them is much less important than what they tell us about the origin and the subsequent history of the solar system. Then there are the comets. Comets include the most distant known objects that are gravitationally tied to the sun. It appears that comets are primarily composed of frozen liquids and gases such as water and methane and ammonia. For most of their lifetimes, comets are just frozen snowballs. They're in deep space. It's only when they approach the sun that the spectacular tails of vaporized materials form. Comets generally have extremely elliptical orbits. It's been suggested that their average distance is about 50,000 times the Earth-Sun separation. That's about 3/4 of a light year. Now, Dutch astronomer Jan Oort, he lived from 1900 to 1992. He suggested that a large number of comet-like objects are found at that distance in a concentration that's now called the Oort cloud. And according to this model, objects from the Oort cloud are occasionally jostled out of orbit, and they begin to fall toward the sun as a comet. A typical orbit from such deep space might take 10 million years. So if the orbit's further perturbed by a large planet, the comet can adopt a shorter orbit near the sun. So Halley's Comet, for example, has a period of only about 75 years. That's a clear indication that the comet was perturbed from what was once a much longer orbit. Now, once a comet's knocked into a new orbit that brings it closer to the sun, Jupiter evidently can exert a very large additional perturbation. That fact was dramatically demonstrated by comet Shoemaker-Levy. That was the comet that collided with Jupiter in mid-July 1994. You know, it started out as a single comet, but the tidal effects of Jupiter broke up the comet into more than 20 fragments, and they one by one smashed into Jupiter. And you could see some of the impacts from Earth. Those collisions each released more energy than hydrogen bombs. They also brought up gases from deep in the Jovian atmosphere, so it was a pretty interesting way to probe the planet Jupiter. There's another really interesting aspect of comets that you may see in the news. A recent controversy has arisen over the possible abundance of relatively tiny comets. These are snowballs. They're just a few meters across. Now, according to astronomer Louis Frank of the University of Iowa, such comets constantly bombard the Earth, perhaps as many as 10 impacts every minute. And Frank based this claim on his studies of satellite measurements of local variations in ultraviolet emissions, which he observed from the upper atmosphere. He observed frequent little energetic puffs that seem to be coming from the atmosphere, and he interprets these events as impacts of comets that just sort of poof out of existence when they hit the upper atmosphere. Each individual event is unimpressive, but over time, he says, these contribute significantly to the total water budget of the planet. After all, 10 impacts per minute of objects up to a few meters across, that could really add up after millions of years. But many other scientists are unconvinced. They disagree, saying Frank's data are flawed, that all he's seeing is instrumental noise. And one of their more compelling counter-arguments is that if such comets are common, then the surface of the moon should be constantly bombarded also. Constantly bombarded with these little comets that just plow into the surface. After all, the moon has no atmosphere to slow them down, so there should be at least a small amount of water at the moon's surface. But every single measurement indicates that the moon is absolutely bone dry, so it's hard to reconcile that with a steady rain of small comets. You know, I've been really surprised at the rancor that's involved in these debates, which have turned quite nasty at times. Each side has claimed that the other is closed-minded, and to me, it just seems like an interesting and a fully testable hypothesis. Well, however the debate turns out, we still have a lot to learn about smaller objects in our solar system. Now, before turning to Earth, let's examine one other very hot area of planetary research, and that's the search for extrasolar planets. With powerful telescopes, we have, for the very first time, the opportunity to detect the presence of planets orbiting relatively nearby stars in the Milky Way. It's not generally possible to see these planets directly, But there's a very powerful technique that reveals their presence. And this technique involves looking for a slight periodic wobble that's caused by a star and a large planet that basically they're orbiting about a common center. Now the Sun, for example, wobbles slightly in unison with Jupiter. So here's Jupiter, but the Sun actually wobbles too. What this means is that the Sun moves back and forth relative to Earth by a few meters per second, depending on where Jupiter is in its orbit. Now that's really a small effect, but astronomers have figured out a way to measure it. Here's what they do. They take an incredibly high-resolution spectra of a star over a period of several months or years. From those spectra, they measure redshifts of a tiny fraction of a wavelength. Those shifts correspond to a relative star motion of a few feet per second towards us or away from us, just a fast walk. And when they plot the pattern of redshift versus time, they see regularly repeating patterns like this one. If there's one big planet in a near circular orbit, the pattern is a perfect sine curve like this. What you're seeing here is a date on the horizontal axis and a redshift or velocity on the vertical axis. Now, if the planet's in a highly elliptical orbit, then the sine curve looks like this, sort of skewed. And I think the really most exciting discoveries are recent patterns that show 2 or 3 extra wiggles, just like this. That's clear evidence for a multiple planet system, a distant solar system. By the way, all these graphs were produced by Paul Butler. He's my colleague at the Carnegie Institution. Paul and his co-workers have discovered more than 40 planets the size of Jupiter or larger, and more are being found every month. They have a great website. It's www.exoplanets.org. You can get an update on all the latest planets there. They've only been doing this for about a decade, and it takes at least that long to map out the orbit of planets with a decade-long period like Jupiter. So new planets are being added all the time. This is an incredibly exciting area of research, and I'm sure you're going to hear a lot more about it if you watch the science news. See, it's now obvious that planets are relatively common out there. Ultimately, we'd really like to be able to take pictures of extrasolar planets. And so there's a new generation of space telescopes that are now in the planning stage. They're designed to image the planetary systems of nearby stars from an Earth orbit. These instruments are called interferometric telescopes. What they do is they synchronize the light gathered at 2 widely spaced mirrors, and that increases the angular resolution. NASA actually has plans to build a space telescope with 2 mirrors 100 meters apart. And that instrument may be big enough to pick out an Earth-like planet orbiting nearby stars. That would just be amazing. And equally important, such a telescope could take the spectra of the planet and might be able to actually resolve the element oxygen in an atmospheric spectrum. Many scientists think that the presence of a lot of oxygen in a planet's atmosphere would be a clear sign of life. So there's obviously a tremendous amount to know about other planets. But now I want to shift focus to our own planet Earth. The Earth is in many respects like the other planets of the solar system. Think about it. For one thing, the Earth orbits in the same plane, in the same direction as the other planets. That's the plane that reveals the average rotation direction of the original solar nebula. We also know from radiometric dating that the Earth formed more or less at the same time as the other planets and the Moon. The condensation of the solar nebula occurred about 4.6 billion years ago. And then the Earth is composed of the same chemical elements as the other objects in the solar system. And of course, it obeys the same physical laws. In fact, in many respects, we see that the Earth is just another planet, and some people might even argue it's a rather small and an insignificant planet at that. But the Earth is also unique in that it has extensive deposits of liquid water on its surface. By theories of origin of life, water plays a central chemical role. Water is the essential medium for all life as we know it. So in that respect, the Earth is a pretty special place. Many characteristics of Earth seem particularly well suited to a habitable surface. And I have to be careful here, I know. Earth is the only place we know of in the universe that has life, so of course it's well suited to life. But think about some of the features of our planet. For one thing, Earth is about 150 million kilometers from the Sun. That's a very special distance. It's close enough to maintain liquid water over most of the surface, but it's not so close as to boil the water away. And then there's the 24-hour rotation period. That's short enough to prevent extreme temperature contrast between night and day, but it's slow enough to prevent extremely violent weather patterns of the kind we see on Jupiter and Saturn. And then there's a matter of size. The Earth, with a radius of 7,000 kilometers, is large enough and has a high enough gravity that fast-moving water vapor molecules can't escape the planet as they do on Mars or the Moon. So Earth has retained most of its water for 4.5 billion years. It's very possible that all of these features, distance, size, orbital characteristics, and more are essential if a planet is to have life. Since we only have a sampling of one so far, it's really difficult to know for sure. Let's turn our attention for a moment to the Earth's earliest period. That's a time called the Great Bombardment. I want you to imagine that amazing time in Earth's early history. Now recall, the solar nebula condensed into the central sun in lots of small planetesimals. And then as the planetesimals clumped together, you had larger protoplanets forming at the expense of smaller chunks of rock. In the final stages of Earth's accretion, the surface must have been a hellish place of glowing molten rock with volcanoes spewing gases and the surface constantly blasted by an incessant rain of comets and asteroids. Every one of the countless objects that was raining down from space, they converted their gravitational potential energy into heat. You know, I'd love to have been some distance up in space looking down at that spectacle. As the bombardment slowly subsided over 100 million years or so, the red-hot molten sphere gradually cooled. And you can imagine a black, rocky crust appeared, though it was constantly being broken both by volcanic activity from below and late impacts from above. Very slowly, the Earth's surface became solid and cooler. All the intense volcanic activity pumped nitrogen and carbon dioxide, water and other gases into the young atmosphere. That's where the atmosphere came from, as well as the water that eventually filled the ocean basins. Scenarios of that stage often include incredibly, unbelievably violent thunderstorms. Now eventually, as the surface cooled in places to below the boiling point of water, torrential rains would have flooded the land and ocean basins began to fill. Still, the surface wasn't home free, because more than once a giant late-stage impact would have blasted away all the oceans and atmospheres. That includes the largest impact, the one that formed the moon. And then you'd have to start making the atmosphere and the oceans all over again. Now, the Earth's interior was also an extremely dynamic place. Take a look at this. Deep inside the molten planet, there are different kinds of material that began to separate by the process of differentiation. Now, we've seen this kind of chemical separation before. Remember, petroleum is separated into lots of different products with heat and distillation columns. And recall the solar system features rocky inner planets and then gaseous outer planets. That's also differentiation. Well, differentiation of a somewhat different kind has given the Earth a radially layered structure, not unlike an onion. In the Earth, gravity and melting drives differentiation. Think of the early Earth as a huge molten ball of different liquids that don't mix like oil and water. So the densest material, that's primarily molten iron and nickel metals, sank down to the center of the growing planet. Ultimately, this metal core increased in size to a sphere about 3,470 kilometers in radius. Okay, so this is like a compressed ball of metal. This dense core represents only about 17% of the solid Earth's volume, but it's almost a third of its mass. It's also more than half of the Earth's radius because it's at the center. Now, most of the remaining material, that's about 80% of the volume and 2/3 of the mass of our planet, form the Earth's mantle. The mantle is made primarily of just 4 elements. About half of the atoms are oxygen. By the way, that's true in the crust too. Oxygen is the main element. And it's pretty surprising. But think about it. Beach sand is silicon dioxide. That's SiO2. And then in the mantle, other major elements are silicon, magnesium, and iron. Now, much of the lightest material formed a relatively thin crust, typically less than a few tens of kilometers thick. The crust concentrated lots of elements, including sodium and potassium, aluminum, hydrogen, and other elements that don't tend to form dense minerals. So that material just sort of floated up and it collected at the surface, very much like slag in an iron furnace. Well, you can ask, how can I possibly know all this? How can anyone tell what's going on inside the Earth? One thing I can tell you is there's no way anyone is ever going to venture down more than a few miles inside the Earth, much less to the center of the Earth. Based on everything we now know about the properties of materials and the effects of temperature and pressure on living things, a journey more than 2 or 3 miles down is inconceivable. So all of our data on the Earth's deep interior are obtained indirectly. And of those indirect methods, seismology is by far the most important. See, seismology is the study of the Earth's inner structure using sound waves, or what are called seismic waves. That's the kind of waves generated by earthquakes. Seismology provides our clearest picture of the Earth's deep interior. Here's a picture that represents sound waves traveling through the Earth's interior. Sound waves pass through the Earth at speeds typically of a few kilometers per second. The speed differs for different kinds of materials, and for a given mineral, the speed is higher at higher pressures where the mineral is denser. Now, in general, the speed of seismic waves increases through denser or colder material, and it decreases through material that's less dense or hotter or partially molten. Now, notice this distinctive pattern. These waves bend. See that as materials change density with depth? Also, waves may be partially reflected off abrupt changes in material, like at the core mantle boundary. So anywhere there's layering, the seismic waves may echo off that discontinuity. Now, there are two kinds of seismic waves that provide information. They're primary or P seismic waves. Those are compressional waves. Recall that in these waves, the motion of the medium, in this case rock, is in the same direction as the motion of the wave, as when you push on something. P waves can travel through solid or liquid, and they carry most of an earthquake's energy. And then there are secondary or S seismic waves, which are kind of shear wave. In these waves, the motion in the medium is at right angles to the direction of the wave motion, as in a wave at a football stadium. You know, you've seen that on Saturday afternoons. One consequence is that S waves don't travel very far in a liquid. See, in a liquid, molecules aren't strongly linked to each other, so a sideways motion doesn't get passed on efficiently. You can see one of the consequences of that in this figure. Some S waves just stop at the core mantle boundary. That observation reveals that the outer core is actually molten iron. P waves generally travel faster than S waves, so they arrive first after an earthquake or other shock. So an earthquake may have one kind of motion followed by a second kind of motion. Most seismic waves are generated by earthquakes, which are sudden movements of rock. That usually happens when stress causes rocks to crack in the crust or in the upper mantle. Now, seismic waves are measured by instruments called seismometers, and they're sensitive to slight vibrations of the earth. A typical seismometer will have a weight suspended on a sensitive spring balance, and any slight jiggling of the ground, even a person walking nearby, can cause a slight ground movement that are amplified by the seismometer. The nose motions are recorded electronically or on a strip chart. You've probably seen pictures of the wiggly lines in a long piece of paper that indicate the onset of an earthquake. Anyway, seismic waves as measured by seismometers reveal details of the Earth's interior. Let me review the major layers. It turns out that the core is divided into these two distinct and separate layers. There's the solid metallic iron inner core, has a radius of 1,200 kilometers, and the maximum pressures at the Earth's center approach 3.5 million atmospheres, and the temperature probably exceeds about 5,000 degrees centigrade, though that number is a little less certain. Then the outer core is liquid, through which the S waves cannot pass. The outer core is formed primarily of iron-nickel metal, but there must be a small amount of one or more lighter elements because the density isn't quite high enough for pure iron-nickel metal. The identity of that light element or elements of the outer core is a hot research topic. It's one of those as yet unanswerable questions that allows scientists to propose highly speculative models. So every so often someone comes up with a bit of new data and they propose that it's oxygen or it's hydrogen or it's sulfur. I remember when I was a graduate student, a classmate came up with what seemed like at first like a really wild idea to put potassium in the outer core. Well, he did a bunch of calculations and got that published with a lot of accompanying publicity. And at least for now, no one's going to prove him wrong. Turns out the origin of the Earth's variable magnetic field is also a matter of some debate. A leading hypothesis is that the field arises in the outer core as liquid iron convects and sets up electrical currents. Now, that's not an unreasonable idea, since magnetic fields arise from electric currents flowing in a loop. Okay, so moving outward from the center, the core mantle boundary may be one of the most complex and fascinating zones of the deep Earth. Seismologists often see strong scattering of seismic waves at this boundary, but the effects are irregular, and the boundary isn't at one distinct depth. So these and other observations have led some geophysicists to suggest that giant 100-kilometer tall mountains, if you will, of relatively lighter minerals may float on the surface of the metal liquid outer core. Now, that's just an amazing idea, that there are mountains on the liquid core. That's another hot topic at geophysics meetings these days. Then we come to the Earth's mantle. The mantle is divided into three major layers, each of which is bounded by seismic discontinuities. The lower mantle extends from about 670 to almost 3,000 kilometers deep. It contains more than half of the Earth's volume. In spite of the fact that the mantle is composed of what's called solid rock, the lower mantle is a dynamic region that will, as we'll see, it drives much of geology at the Earth's surface. That's because hot rock is plastic. It can actually flow slowly if it's put under stress. So over long spans of geological time, the mantle convects. And then between about 400 and 670 kilometers deep is the transition zone of the mantle. That's a region distinguished by a dramatic increase in seismic velocities. Now, most geologists assume that this change in physical properties is associated with phase transformations of low-pressure minerals into high-pressure forms that are very dense. And this idea ties in with the great principle that properties of materials are a consequence of their atoms and how those atoms are bonded together. By the way, a lot of my own research at the Geophysical Laboratory is focused on the unusual minerals that make up this interesting transition zone. And one of the most distinctive aspects of these structures is that the lower pressure minerals have silicon atoms surrounded by 4 oxygen, but they transform in the transition zone to higher pressure forms where the denser packing atoms, silicon atoms, become surrounded by 6 oxygen atoms in these denser form. And then there's the upper mantle. That's above about 400 kilometers deep. The upper mantle features the same relatively simple composition of the entire mantle. The upper mantle is dominated by just 4 elements: oxygen, silicon, magnesium, and iron. But here, these 4 elements occur in relatively low-density minerals typical of the crust. Some of these minerals are garnet and pyroxene and olivine, all of which are common constituents of some crustal rocks. Finally, seismology that's been coupled with centuries of geological field studies and mining and deep drilling reveals that the Earth's crust is an extremely heterogeneous place. The crust has wonderfully complex structures that point to a very dynamic history. The crust is compositionally quite varied. In some places it's made of black volcanic rock, like basalt that pours from those great volcanoes in Hawaii. In other places we find many miles thickness of sediments that were deposited by erosion as particles in layer upon layer upon layer. Those sedimentary rocks are often rich in fossils, and I'll tell you a lot more about crustal rocks in Lecture 42. The crust features all sorts of complex structures that point to a dynamic and an energetic interior. Layers of rock that were once flat are now seen to be disrupted by complex folding, as well as fractures called faults. Erosion by wind and water, it carves the Earth's surface into its present landscape with mountains and valleys. All in all, I think we live on a pretty fascinating planet. Before I conclude, I want to tell you about what I think is one of the neatest ideas I've heard about for probing the Earth's deep interior. Now, this is a wild proposal to use neutrinos as a probe of the entire Earth. Now recall, neutrinos are particles that are produced in prodigious quantities in nuclear reactions in the sun. Neutrinos have very little mass and no electrical charge, so they pass through most matter. In fact, every second, countless neutrinos from the sun pass through the entire Earth. But there is a slight absorption. In fact, it's likely that different elements absorb neutrinos differently. For example, iron or oxygen might absorb neutrinos of certain energies more efficiently than other energies. And different elements should have their own distinctive neutrino absorption spectra. So there exists the prospect of developing a kind of neutrino absorption spectroscopy, which works because the entire Earth selectively absorbs neutrinos. So you'd need a giant orbiting neutrino observatory, which would take measurements on the dark side of the Earth. So solar neutrinos would pass through the Earth, some of those neutrinos would be absorbed, and the resulting filtered neutrinos would be measured. So that way, for example, we might be able to detect the light element in the outer core, or maybe see the compositional shadow of those mountains at the core mantle boundary. You know, it's a wild idea and it won't likely happen anytime in our lifetimes. But it's nice to know that there's still so many exciting and novel things to try in the world of science. Well, to summarize, this lecture has featured the transition from the solar system in general to our home planet in particular. We've seen that Earth is a rather ordinary object in some respects. It's like all the other planets in many details of its orbit. It's like all the other terrestrial planets in terms of its bulk composition and size. But Earth is also a very special world. Its distance from the sun, its rotation period, and its size seem ideally suited to the maintenance of life. Unlike any other planet today, Earth has oceans of liquid water and a stable atmosphere that maintains a large habitable zone at and near the surface. It's pretty nice to have Earth as a place to call home. In the next lecture, I'm continuing to focus on Earth. We'll see that the distinctive features of Earth's surface reveal that we live on a remarkably dynamic planet.